Welcome back to The Foundry, an explainer series brought to you by Forge College. Our topic today is a hands-on SegWit transaction demonstration. Now, in our previous explainer, how SegWit addresses malleability and improves throughput, we spent a lot of time on the abstract theory of segregated witness. We talked about how it works and why it matters. But, theory only gets you so far, right? So today, we're putting on our hard hats, rolling up our sleeves, and moving straight from the whiteboard to the workbench. We're going to conduct a tangible, hands-on engineering lab experiment with SegWit. We'll construct a real transaction from scratch, inspect the raw data, and see the exact mechanics at play in real time. It's going to be a lot of fun. To keep us on track, let's quickly run through today's blueprint. Step 1, welcome to the lab. Step 2, building the transaction. Step 3, splitting the base and witness data. Step 4, the mutation experiment. And finally, Step 5, measuring weight. Let's dive right in.
All right, Section 1. Welcome to the lab and setting up our sandbox. Now, right off the bat, if you're kind of worried about accidentally breaking the main Bitcoin network or losing real funds, take a deep breath. We are doing this in a highly secure, isolated testing facility called regtest. Absolutely no Bitcoin police here. Setting this up requires 3 super simple steps. First, we start our node in regtest mode. Second, we create a dedicated testing wallet, which we've creatively named SegWit Demo. And third, we mine exactly 101 blocks. You might be wondering, why 101? Well, newly minted test coins actually need to mature before we're allowed to spend them. It's basically like printing our own Monopoly money before we can start playing the board game.
Moving right along to Section 2, building your first transaction, which is basically our assembly line. So think of this process like a literal assembly line where we're constructing a high-performance engine. But before we start bolting things together, we really need to address this slightly intimidating acronym, PSBT. That stands for Partially Signed Bitcoin Transaction. It sounds super complex, but honestly, it's just a digital permission slip being passed around a classroom. Everyone can read the transaction details and safely add their signatures or witness data, but nothing is actually executed until the teacher locks it all in at the very end. It's just a really safe, standardized way to collaborate. Here is our actual step-by-step assembly sequence using that PSBT format. First, we create the raw transaction. That's just drafting the empty shell. Second, we convert that shell into our PSBT permission slip. Third, we sign it. This securely packages our absolutely crucial witness data. And finally, we finalize the whole thing to get the raw hex code. This chain of commands handles all the complex cryptographic packaging behind the scenes, leaving us with a perfectly constructed SegWit transaction.
Which brings us to Section 3, splitting the base and witness data. I like to call this the autopsy.
It is time to visually slice our newly built transaction right down the middle to see what SegWit actually, segregated. This brilliantly illustrates the core magic of the upgrade. When we split it open, we see 2 parts. First, the base data. And notice how the old legacy signature space is completely empty. Then, completely separated out, we have our witness data, which safely holds our signatures and public key. Think of the base data like a car's physical chassis and its unchangeable VIN number. The witness data, that's like a sleek aerodynamic roof rack you just bolted onto the top. It holds your luggage, your signatures, safely outside the main chassis.
All right, Section 4, the mutation experiment. It is time for some stress testing.
This is where we get to put on our metaphorical mad scientist goggles. We've built this perfect transaction, and now we're going to try to break it. Seriously, what happens if we intentionally flip just a single byte in the witness data? Imagine an attacker maliciously messing with the luggage sitting up in our roof rack. What actually happens to the transaction itself? I want you to really think about this for a second. What will our nodes say?
Let's reveal the magic. The result is exactly what we hoped for. In our original transaction, we had a primary ID, let's call it txid-A, and a witness ID, wtxid-B. After we deliberately flipped a byte, our mutated transaction has a brand new witness ID, C, because the signature data changed. But the core transaction ID, txid-A, it remains completely 100% identical. Even after altering the witness data, the core license plate of our transaction didn't flinch. This proves unequivocally that the dreaded transaction malleability attack is totally neutralized. You can mess with the luggage on the roof rack all day long, but there's absolutely no way you can change the car's VIN. SegWit works exactly as advertised.
Section 5, measuring weight and size, the final measurement.
So we just proved the security benefit against malleability, right? Now let's prove the network throughput benefit.
We need to look at how transaction weight is calculated now. The formula for weight is the base size multiplied by 4 plus the witness size. Then, the virtual size, or vsize, is just the ceiling of that total weight divided by 4. By taking that heavy signature data and literally pulling it out of the base transaction, SegWit artificially shrinks the transaction's virtual footprint. And that is exactly what allows us to fit significantly more transactions into a single block.
The absolute key to this whole shebang is the number 4. The base data gets penalized. It gets multiplied by a weight of 4, but the witness data does not. This mathematical discount applied to the witness data is the exact mechanism that supercharges the Bitcoin network's throughput. It's honestly just an elegant bit of software engineering that solved a massive scaling problem, and it did it all without requiring a hard fork. And just like that, our lab experiment is a complete success. We've proven firsthand that SegWit prevents malleability by segregating the witness data, and it boosts throughput via that really clever weight discount. But before we wrap up, I want to leave you with a thought. If we can segregate signatures to save space, what happens if we start mathematically hiding complex smart contracts inside those signatures so they just look like standard boring transactions? Well, that is the magic of Taproot. If you love getting into the nuts and bolts of blockchain engineering like this, I highly encourage you to visit forge.college. You can continue your Web3 learning journey and dive into Taproot with us. Thanks for joining this explainer from Forge College. Keep building, keep experimenting, and I will see you in the next one.